Hello everyone, good morning. Welcome back to the expert lecture series by the Department of Mechanical Engineering, Francis Xavier Engineering College, Tirunelveli. Let me brief on the campus and department profile. Francis Xavier Engineering College, fondly referred as FX Engineering College, was established in the year 2000 and is located down south of Tamil Nadu in Tirunelveli district. It is an educational wing of SCAD Group, a socially committed group which works for the upliftment of underprivileged and marginalized community and founded with a vision of reaching the unreached. In Francis Xavier Engineering College, we offer 6 UG programs, 10 PG programs, and have research centers offering doctoral programs. The campus is ideal for learning and character building. Our institution has received grants from various funding agencies to carry out the state-of-the-art research and for conducting training programs and workshops for students and faculty members. Francis Xavier Engineering College has been offered the autonomous status in the year 2019 for a period of 10 years. 4 of the undergraduate programs are accredited by NBA, the National Board of Accreditation. FX Engineering College believes in the holistic development of the students and faculty members. The Department of Mechanical Engineering was started in the year 2005 and offers BE in Mechanical Engineering and ME in Industrial Safety Engineering. The Department of Mechanical Engineering is the largest on campus with good infrastructure in terms of laboratories and other amenities. The department is NBA accredited and permanently affiliated by an university. The department has got experienced and passionate faculty members with rich and diversified domain expertise. In addition to the courses enlisted in the curriculum, many value-added courses have been offered to the students to broaden their technical knowledge. The students are offered with adequate hands-on training to equip them with the requisite skill sets, making them industry-ready technocrats and entrepreneurs. Special applied laboratories have been established, encouraging student innovation. We also have Academy for training students to appear for GATE exam to get into premier institutions like NITs and IITs for higher studies or to get job in public sector units. The jewel in the crown is we are ahead in breaking gender stereotypes. We have many girl students and women faculty members doing remarkably well in the so-called male-specific stream of engineering, that is mechanical engineering. Thank you. Hello again, this is Dr. Farida, Professor in the Department of Mechanical Engineering, Francis Xavier Engineering College, Tirunelveli. I'll brief on the profile of today's speaker, Dr. Liza K. Elliott. Dr. Liza is a Senior Research Associate in the Department of Chemical Engineering at the University of Newcastle, New South Wales, Australia. She earned her bachelor degree B.Hons in Chemical Engineering from the University of Newcastle in the year 1993. She completed her PhD in the year 2000 from the University of Newcastle, Australia. Her PhD was on lime dissolution in coal ash slag in integrated gasification combined cycle. Dr. Liza is a combustion engineer at the University of Newcastle in the Combustion Center, CCSD, in the Department of Chemical Engineering. She has worked on various aspects of coal combustion for the Australian coal industry for more than 25 years. Her research areas are on coal combustion and pyrometallurgy. She has a significant experience in ash and boiler deposit formation analysis and PCA in blast furnace. She has developed new techniques to show the formation mechanism and life history of deposits and techniques to assess cools for potential blockages in PCI lines. She has published a good number of research papers in peer-reviewed journals and has received many research grants from Australian government for coal research. Her current funding projects include combustion predictor for thermal coal utilization in pulverized fuel boilers, mineral redistribution from PF coal to ash in commercial power stations, and slagging and fouling during co-combustion in high efficiency and low emission boilers. Dr. Liza is with the University of Newcastle for the last 30 years, starting as an undergraduate student. The University of Newcastle has a strong history of supporting coal research, which is a key component of Australian economy, which she is proud to continue. Dr. Liza, an expert in coal research, is among us today. Let us make use of this session effectively. I'm sure the lecture is going to be very interesting and informative. I also would like to extend my warm welcome to all the participants, the viewers. I hand over the session to the speaker, Dr. Liza K. Elliott. Over to you, Dr. Liza.
Hello to Francis Xavier Engineering College, and thank you for having me. I hope that you find this interesting. I've aimed this at engineers who haven't got experience in coal. So if If it's a little bit low for you, I apologise. All right, so we're here to talk about the basics of coal combustion. To understand coal combustion, you really need to understand what you're burning. So you have to have an understanding of coal. Coal is a sedimentary rock. It forms from vegetation that's been captured under the earth for a significant period of time. The longer the time, the blacker the coal that forms. So it takes heat, pressure, and time to form coal. Okay. The coal that does form is a function of where it's made. So coal generally is made in boggy areas. So areas where water covers the ground pretty consistently. If it forms in areas where water, where the ground is completely submerged to a large depth for a very long time, you have no oxygen content and you end up with putrefied, muddy material. If it's formed in dry forests, rotting occurs. And so anything that does form to coal is usually very woody or has a large amount of resin in it. The places in between where water comes and goes or is there and at low levels across the ground is really where peat forms, and that's what forms and turns into coal. So you end up with humic material that eventually, with time and pressure, becomes coal. If coal's formed under salt water, it will contain a large amounts of sodium and chlorine. So where it forms makes a big difference, and what the material is that forms the coal is very important. At the bottom there, you will see the lithotypes. That's what geologists use to describe on a macro level the seams that form. So that's a macro description. So what happens when coal forms? Heat that has a lot of organic matter in it, which is will move slowly to form things that are far more graphitic in nature. So rings of hydrocarbons become closer and closer, and those things that bridge between those rings are removed. So, or things that are hanging off the side of them are removed. And so eventually it becomes more graphitic. So you're losing oxygen, nitrogen, and hydrogen, especially. Okay. So as you become more coal-like, or the rank of the coal increases, you're going to lose things like moisture. So it's going to get less moisture contained in it. You're going to lose the volatile content, and that's the stuff that will come out of the coal when you heat it. So those are the low molecular weight hydrocarbons, the things that are hanging off the side, and the things that bond between the rings of the aromatic rings. You're also going to increase your fixed carbon content. So this is your the actual rings, the carbon in the rings that you've got in your coal. That's going to increase as the coal becomes of a higher rank, and the actual energy associated with your coal will increase as well. The thing that on the right here, the vitrinite reflectance. The reflectance is a measure of how it reflects light, and that is what is used generally to determine what rank your coal is or how close to graphitic in nature it is. Okay. Oh, the other thing I should say is as you increase in rank, you will decrease the ash content. So things like sodium and potassium, which are very common in low rank coals, are not so common in the higher rank coals. And they're things that are usually attached to those carbon chains. So you will lose them as well. So generally when we're talking about coals, we're trying to talk about their rank. And so we're talking about that amount of rings in the coal structure. And so a lower rank coal, a lignite or a brown coal, will have more interconnecting chains, and they will have far more ash and far more moisture. So this type of graph which we have here, this is called a Saylor's chart. This was developed by a British geologist, and most coals will fall into these ranges, although classification of the coals does vary from country to country. Okay. But within a coal, there are different things as well. So within the carbon structure, there are things that will change based on where that coal has come from or what part of the plant that coal has formed from. So these are called the macérals. We generally, a geologist will look right down to the fine grain to find out which bit has come from where, but us engineers tend to work on the group. And so we'll be looking at the liptonite content. That's in America, that's called exonite, the vitrinite content and the inertinite content. The liptonite content is the most reactive part of the material, but in Australian coals, there's usually very little of it there. In vitrinite, the vitrinite content is the next reactive part, and the inertinite content is the least reactive. It was originally called inertinite because it was considered to be very inert and it really didn't do anything. But in the last 20, 30 years, they've really shown that inertinite has quite a high reactivity, not as high as all of the vitrinite. And so vitrinite and inertinite have been found to actually overlap. The lower, less reactive parts of the vitrinite will be less reactive than the highest reactive parts of the inertinite. But in general, on average, the vitrinite is more reactive than the inertinite. And the reactivity of those materials will change depending on the rank of the coal. Okay. If we look at the coal under a microscope, you'll see particles that kind of look the same. But the big point here is if we divide them up into vitrinite and inertinite, which we will here, the yellow ones are the inertinite, the green ones are the vitrinite, the red coloured parts are minerals. So you can see that some particles are all inertinite, some particles are all vitrinite, but there's also particles that contain both. And the really big point to take away from this is coal is not a single material. It's a range of material. In fact, every particle in the coal will differ. And so you can never talk about coal as one material. It always is a range. And quite often the issues you come across because of the combustion of the coal is a function of one part of the coal, not the whole lot. Though most people will talk about the coal as an average. So, coal is not a simple material. Don't think of it as such. To add on top of that, within those coal particles, there's also minerals. So if we go to have a look at this, this is an SEM image of coal sample. You can see the dark red material is coal, is the carbonaceous material. All the other colours are the minerals in the coal. Now, it's not a consistent colour across it, so that shows you that the minerals are there in individual particles or in particles on their own where they've been liberated from the carbon material during crushing. So again, you can't look at a coal and say it's an average material. Every bit changes, and you really have to be considerate that it's a heterogeneous material. Okay. All right. So we know what coal is now. Where do we use it? Coal is generally, the two main largest uses of coal is power generation and steelmaking. Power generation in Australia anyway, they're generally done in what's called pulverised fuel boilers. And I think that's pretty much the most common use of boiler around the world. So in these, coal is fed in through the boilers, through the burners, sorry, into the radiant section, which is this section here. Radiant section is any part that sees the flame. The combustion gases then leave the radiant section and head off, go up through the boiler and come up through this area here and then out. The boiler is really a very large heat exchanger. Each surface of the boiler, all the walls are covered in tubes, And in the top area, in the convective bank and the economizer, these areas here, the tubes hang down into the gas stream in an effort to get as much heat out of them as possible. And those tubes raise steam, and the steam is then taken to a turbine to generate electricity. So the things to note about using coal in here is that it's a combustion process. That is, it's an oxidizing process. There's always excess oxygen. So the coal will always be looking to be burning out. The issues associated with this boiler, or this type of boiler, is hotspots forming in the radiative section where the coal is burning too fast and that area gets too hot. And that can have big issues on the tubes, particularly the material that the tubes are made out of. If it goes too hot, they can be deformed and they can eventually leak, which is a disaster. Other issues are carbon in ash. So when the ash comes out the exit of the boiler, there could still be unburned carbon in it. And that's an indication that you haven't got all the energy out of it. It hasn't had enough reactivity. And then the other issue, which is pretty big, is deposition along the tubes. About 10% of the ash that's produced in the combustion of the coal hits and remains on the tubes rather than leaving with the combustion gases. So if they are allowed to sit on the tubes for too long, they will actually sinter, possibly melt, form strength and be impossible to remove. And having an extra layer on your tubes affects your heat transfer. So you won't be able to get the heat transfer you're expecting if you keep building up a layer on those tubes. So they're the big issues. The other thing I should tell you about these is that the coal particles themselves get to about 1800 degrees in this boiler, and they have a heating rate that's in the flame of about 10 to the 4 degrees per second. So it's a pretty fast heat up. It's a pretty high temperature to produce that sort of steam that they need. All right. The other use that we predominantly use coal for is steel making. To make steel, you need iron, and iron is generally made in a blast furnace. So to make iron, you make coke, put in layers of coke and iron ore into the blast furnace. And as the iron ore is reduced and the coke is consumed, those layers move down through the furnace, allowing more layers to be put in on top. Now that coke is made in a coke oven. So the coke oven over here. So the coal is fed into the oven, it's sealed, it's heated, and then the coke goes through a change where the volatiles are driven off. There is a liquid layer form that allows the coke to swell, and once it's all finished and is cooled down, the coke is actually structurally very hard, and that has strength that's able to support the extra weight on top of it when it goes into the blast furnace. In the blast furnace, the oxygen or hot air is introduced through the tuyeres. That initially combusts some of the carbon there, some of the coke, or they inject coal in through the tuyer as well, so that you can produce a lot of energy, because the rest of the reactions inside a blast furnace are endothermic. So you need heat to actually get things going. So once you get that heat going, the carbon can be used to produce CO, and that CO will reduce the iron ore to make iron. So, okay, the issues that we have here, in terms of PCI, so I should just mention PCI, the coal that goes into there will experience very, very fast heating rates. We're talking about 10 to the 5 to 10 to the 6 degrees per second. It will also experience very high temperatures. We're talking about 2,200 degrees in the raceway area. So the coal that goes in there, if it's not reactive enough, because it's only got about 20 milliseconds to get across that raceway, if it's not reactive enough, and it does reach the end of the raceway, it has potential to block up the rest of the bed because the gas has to travel through that bed to get out. And if you block the rest of the bed up, you don't get gas travelling through, you don't get reduction. So that is the big issue for PCI. For coke, if you can't make a coke of good strength, the bed will collapse and you again won't get gas flowing through your bed. You don't get gas flowing through your bed, you don't get reduction. Issues for both coke and PCI is chemistry. If you have too much potassium in there, you will end up with potassium attacks the strength of the coke and breaks it down. So you will actually get that reduction in the permeability of your bed. Potassium also attacks the refractories inside the blast furnace. So too much potassium and the coal is not suitable for steel making or for iron making. Anything chemistry-wise that's in the coal, in the coke, or even in the iron ore is going to end up either in your slag or your iron. Silica, for example, dissolves into iron. Most of it will end up in your slag, but there is a proportion in your iron, and if you change that proportion too much, the steelmakers won't love you. If you need to have a particular viscosity of your slag to get it to flow, then changing the chemistry of your slag by changing the minerals that are associated with your coal could have a big impact. So chemistry is very important. Okay. The other one I wanted to mention was gasification. The reason I wanted to mention this is that it really highlights the importance of the atmosphere that the reactions are occurring in. So gasification is used either to make power or to make chemicals. Initially, the coal is injected into a combustion zone where the coal is burnt. That provides heat to drive, again, the gasification reactions. So to make CO and H2. But that has to be done in a reducing environment. So the top of this chamber up here, go back, I shouldn't have clicked. The top of this chamber up here is a very reducing environment where just down here, it's oxidizing in a coal stream, in an oxygen stream with coal. So balancing the chemicals is very important. The other part of this is heat transfer to recover the heat that's produced. So very high temperatures, but very reducing environment. But it does make a very productive gas, and that gas can be burnt in a gas turbine to make electricity, or the gas can be used to generate chemicals, to make hydrocarbons. They're the building blocks for any type of hydrocarbon you want. Okay, so we know where the coal's going to be used. How do we know what coal we should use where? So that is done by characterising your coal. There are a whole heap of standard analyses and there's a range of non-standard analyses. The standard ones, which are pretty much done for almost every coal, except maybe for the coking analyses, which are only done for coking coals, are moisture. There's three types of moisture that you will end up with. Free moisture, which is basically just drying the sample in a room atmosphere. Inherent moisture, where you dry the sample till it's bone dry at a temperature above 100 degrees. And then total moisture, which is the free moisture plus the inherent moisture. There's proximate analysis, which basically gives you the volatile content, that is whatever will be driven off at when you heat the coal. The fixed carbon, so once you've lost that volatile content, what's the carbon associated with those rings? And the ash content. So once you burn a coal, how much of the minerals have converted to ash and what is left behind? The ultimate analysis, that's a chemical analysis which gives you the carbon, hydrogen, oxygen, nitrogen, and sulfur content. The specific energy tells you the energy that you've got in each coal. The ash oxide analysis, so that's measurement of the chemical constituents in the coal on an elemental basis, but reported as oxides. The reflectance, again, very important if you want to know your rank, and that's one of the first questions most people will ask you. The crucible swelling index, the dilatation, and the Gray-King coking value are coking tests. The crucible swelling index is like 120 years old, and it really is just sticking the coal in a crucible, covering it, heating it at a set rate, and then looking at what the coal looks, or the coke button that's finished, looks like afterwards. It's a very old test, and it's really not very valuable. Dilatation, on the other hand, is a way of measuring how much the sample is swelled at a far more scientific way. Gray-King measures the proportion of coke, gas, and tar that you will form in the coke ovens. Coke strength is one of the ones that most steelmakers are really keen on, because if you haven't got enough strength, you are going to have problems in your blast furnace. So it's one that very often keeps popping up. Hardgrove grindability is a great test. It measures how easy a coal is to grind, and it has the worst name ever. It was named after Mr. Hardgrove, but it suggests that the higher the number, the harder the coal, and it's actually the opposite way around. The higher the grindability number, the easier the coal is to grind. And then ash fusion tests. Fusibility talks about how easy it is, or how quickly the ash in the coal is going to form a material that's difficult to remove. So how easy is it to sinter and then form a solid glump of something on the tubes in your boiler that you're going to have to get rid of. Unfortunately, I think it's not a great test either, because it's more reliant on the surface tension that forms and the viscosity, rather than when it's going to melt and what happens when it melts. Okay. And these are the tests that generally happen in research or at universities. So we measure the reactivity, how quickly the carbonate nature of the coal is consumed. We use SEMs, CCSEMs, or TIMR. TIMR is a SEM, an automated SEM, as is CCSEM. So it allows you to look at what is present. So I should say also, an SEM is a scanning electron microscope. So it gives you images of the samples, allows you to see what is present, but also can give you a chemical analysis of the material. XRD is X-ray diffraction, and we do that on what we call a low temperature ash. If you can remove the carbonaceous material at a temperature below 100 degrees, it doesn't affect the minerals that are present, and then you can use an XRD, which tells you the crystalline structure that is there, and that way you can find out what minerals are present. We also measure the viscosity of the ash once it's formed as slag, so we melt it to make a slag and measure the viscosity of it. We use thermomechanical analysis. This is where you measure the change in dimension of a ash as it's being heated. And we use a char particle analysis, where we look at what type of char is forming when you combust the coal, and we measure the surface area. Okay. So what happens when you heat coal? So initially, the first thing that happens when you get to about 100 degree, moisture comes off. If you keep heating to about 450 degrees, depending on the coal, the small chain hydrocarbons will break away, and often they will come off the sample, and they are classed as volatile matter. If the temperature gets above ignition and the atmosphere is oxidizing, these volatile components will spontaneously combust, and then ignition will start. I'm not going to talk about ignition today. I'm going to leave that to Farida. That was her PhD area, and she is by far a greater expert on that than me. The the volatile matter that you do get off, as shown by this graph, is a function of the temperature that you heat it to, the time you're at that temperature, the heating rate you take to get to that temperature, and of course the nature of the coal. So what chemically is actually present in the coal. Okay. But also what's happening to the coal when it's heating. So we're removing those interlocking bonds, those bridges that join between the aromatic chains and the side chains that are on those aromatic rings. When that happens, it interacts with those aromatic rings and the chemical nature of the coal changes. This is called a metaplast. It turns into a liquidy plastic type material. As you can see here on the side here, if you leach the coal before you get to that temperature, you get a small range. This was done on a Maldi, sorry. So it measures the molecular weight of species when it hits it with a laser. And you can see that there's molecular weights. Each one of those lines is a Dalton. So a molecular weight of a 400 Dalton is a ring that has a molecular weight of about 400. And you can see that there's a small amount of material that the Maldi is able to pick up. If you leach a material at a higher temperature when it's gone through this change in metaplast, you can get a whole lot more material off. So there is an actual physical change, a chemical change in the nature of the coal. As you keep going through that range and go beyond it, it then locks in the new nature of the coal to make a far more graphitic structure. And you can see at the bottom here, it goes back to not being able to release much at all. So what happens when you've got this liquid phase forming? If there's enough surface tension and enough viscosity, you are going to be able to capture gas bubbles as they're being released. So if you form things like methane and other low chain hydrocarbons, they are going to be at these temperatures a gas. So as it comes off, these bubbles form and the whole structure will turn into a foam. That means because it's trapping these gas bubbles, the whole coal will swell. And that's what you can see down here on this graph. This red line shows how much swell has actually occurred. And you can see it's about 17%. This coal is a non-swelling coal. This is what we would call a thermal coal suitable only for use in a power station. It wouldn't make a good coke. Coking coals can swell 200, 300, 400 times their original size. Okay. So what happens to the char once you've gone through this metaplast phase? What forms? Well, it depends where it comes from and how much of that metaplast you actually make. So if you're using a coal that's predominantly made of vitrinite, it's more likely, because it's got more hydrogen content, it's more likely to form a metaplast, and it's more likely to form a char that is swollen. Even coals that are predominantly used in thermal power stations will form swollen char material. So this is a coal for a power station. This has come from a vitrinite particle, and you can see it's a bit like a foam. It's a char that's been sectioned across and looked at under an SEM. And it's got large pores, small walls. This one on the right has come from an inertinite particle, and really it has swollen, but it's only swollen a little bit. And you can see the pores that were in the particle initially have only just expanded. So char formation really does depend on which particle it comes from. So you have a char and it's ready to combust. You've got oxygen, you're going to produce CO2. There are 3 steps generally identified in the combustion reaction: chemical control, So that is the actual reaction itself. That's the oxygen reacting with the carbon to make CO or CO2. And the equations for chemical control are here. Then there's diffusion control, when the oxygen takes longer to diffuse to the surface of the particle than it does for the reaction to occur. And they're the equations for diffusion down here. There is a third step, and that's when it's a combination of the two. It's described as the ability of the oxygen to penetrate the surface of the char. And as with all rates, the slowest step controls the reaction. Typically, chemical control is about 150 kilojoules per mole. And you can see here that it's usually a function of the temperature that the particle gets to. So this is inverse temperature. So at lower temperatures, 600 maybe, you're always going to be in chemical control. As you increase the temperature, you're going to get to regime 2, which is called poor diffusion control. That's the combination of the two. And then if you increase the temperature even further, oxygen diffusion will control. Generally for coals, the activation energy here is about 150 kilojoules per mole, and that doesn't change too much at all. But for different coals, the pre-exponential factor really can change. Okay, the other point to make here is particle size really impacts where these boundaries occur between the changes. And so even though PCI occurs at temperatures that you would expect to fall up here, so pulverized coal injection into blast furnaces is what I'm talking about, you would expect them to occur up here because we're talking about the highest temperatures that we see in combustion. Because we're talking about very small particles, it's debatable whether they actually get into oxygen control or oxygen diffusion control, because the smaller the particle, as you can see down here, the higher the rate. So you have to be careful and don't assume it's solely particle temperature controlled. All right. And for completion, we need to talk about gasification, because if you're in an area where you don't have enough oxygen, gasification will occur. The problem is gasification is endothermic, and therefore it's a much slower reaction rate than oxidation. Okay. The other point to make about what happens to the coal is the char will graphitize if you leave it under temperature for long enough. So depending on how long the combustion occurs, you will be changing the behaviour of the char. So when I say that, what I mean is the structure in the coal will continue to change. Even though it's burning, it will actually keep moving towards a graphitic nature. So the longer the reaction takes, the more likely what's left over is going to be unreactive because it's more graphitic in nature. We have two ways of measuring. You can, sorry, I should say that up here. You can see here, we have also the higher the temperature the char gets to, the less likely it's going to be reactive, and it's because it's become more graphitic in nature. We have two ways of measuring the graphitic nature of the char. One is to actually measure the crystalline structures that are formed. We do that using an XRD. So you can measure LC and LA. LC is the height between the graphitic sheets, and LA is the length of the graphitic sheets. And this figure here on the bottom shows you the difference between chars that were produced in a PCR rig and chars that were produced in a drop tube furnace. And there are significant differences in this area, whereas not so much for lower rank, high volatile coals. The other way to measure it is to use the reactivity of the material as a measure itself. What we've done in this one is to measure how much of the coal disappears at each reaction temperature. So at lower reaction temperatures, char that are graphitic in nature are not going to react, where chars that are graphitic in nature will require much higher temperatures to react. So we used a TGA and changed the reaction temperature progressively and measured those changes, and were able to show that the graphitic nature of the char was a function of the density of the starting material. Anyway, the other thing to note is what happens to the minerals. So you're combusting the coal, you have minerals in that coal, and we know they turn to ash, but how do we get there? Each type of maceral will form different types of minerals, but it's also a function of which minerals were there will form different types of ash, but that's a function of which minerals were there at the beginning. So if you have a coal that's predominantly vitrinite or highly reactive liptonite, you're going to form type 1 type chars, and they're very high porosity, very thin walled. Now, if those walls, as that char is eaten away during the oxidation reaction, those minerals are less likely to join together. So the minerals will separate into individual parts of char as the char is burnt out, and they won't join together, and you'll form a very fine ash material. Type 2 chars are intermediate ones. So they're the less reactive vitrinite, the more reactive inertinite. They have smaller porosity, thicker walls, but some of the minerals in the char will have the opportunity to join together because they're close enough in the char and the char is large enough to sustain them together until they reach a melting temperature where they can join. Type 3 chars are the inertinite type chars that don't swell at all. These chars, the minerals will stay within the char as it's being eaten away and will move closer and closer together and eventually form one solid ash particle. So that's important because when you're talking about the deposition in a boiler, the size of the particle that's formed, the density of the particle, which is a function of its chemistry, will depend on whether it deposits on the tube. There are lots of different mechanisms for deposition, but most of them are a function of density, particle size, or the momentum in the gas stream, and also the viscosity of the resulting ash particle. That is how sticky it becomes. And then when it hits the wall, when it gets onto the tube, how thick a layer is it going to form? And how solid is it? How much porosity does it have? Because that will greatly affect how you operate. All right, so in conclusion, the big points that you need to take from this is coal is a heterogeneous material. It's a very varied substance, even in the one coal. And the behaviour of the coal is dependent on its character, that is its rank, the maceral components, the mineral species that are present in it, and where they reside in the carbon structure. And how it's used will affect what happens. So the temperature, the heating rate, the gas environment, and the time at temperature really makes a big impact. That's where I'd like to leave it. Thank you for your time and your patience.
Thank you, Dr. Liza. We'll have a couple of questions from the participants. The first question is on the environmental impact. When we burn coal conventionally, it leads to greenhouse gas emission like CO2 emission, which leads to global warming and climate change. What are the ways to address this problem?
So at the moment with greenhouse, there's so much carbon dioxide produced by one power station. There is no way we could possibly use or utilise that amount of CO2 in any way. So we really do need to change the way that we operate. We either need to find alternative solutions, or we need to capture the CO2 and do something with it. The most common one that I've been involved with, or that we've worked on, is capturing the CO2 by changing the way the boiler works, such that we recycle the off gas back through the boiler to make a stream that's highly concentrated CO2 with very little nitrogen and very little oxygen. So instead of injecting air, we would inject with oxygen and use the recycled flue gas to temper the reaction in the flame, so that it's not all in one very small area and you can still use the boilers that we normally use today. That would give you a reasonably clean stream, like it's not pure, but it's a very concentrated stream of CO2. Then you need to be able to do something with that. Some people have looked at sequestering that underground. It's certainly in Australia, the problem is finding a place that is suitable. Not all places will take the CO2 and keep it. There's a lot of areas where the geology is just not good enough and the CO2 will come back to the surface. There is talk of possibly putting them into aquifers because the CO2 will dissolve in water. Those aquifers, again, will depend on where they go and how close to the surface they are. The best solution so far in Australia has been to use them to increase the amount of oil production in oil wells. You can actually push the CO2 into the oil well and it actually enhances the amount of oil that you can get out. So that's the best solution so far. We have one where they're talking about just sequestering it and not using it for other means in the Otway Basin, but getting approval to do this has been very, very hard.
Thank you. The next question is, what is the difference between thermal coal and coking coal?
Thermal coal is a coal that doesn't swell particularly well or doesn't provide strength when it does swell. So a coking coal needs to be able to swell to produce a quality coke. And once it's swelled and formed a coke, it has to have quality strength. So the measure of its ability to form a coke, that is swell and maintain that strength, is depends on whether you call it a coking coal or a non-coking coal or a thermal coal. Generally, the coals that are very, very high rank, so the anthracites, the semi-anthracites, don't have enough volatile content to swell. The bituminous and subbituminous coals do, but not all bituminous and subbituminous coals will hold their strength. And lignites haven't got a hope. So they are generally bituminous coals, some subbituminous, but usually bituminous coals that are coking coals, but not all bituminous coals are coking coals. Does that make sense?
Yep, lot of sense. And the next question is, are pyrolysis and devolatilization same?
Yes, pretty much. So when you pyrolyze a material, you're removing the volatile content. So you're devolatilizing the material. So yes.
Okay. Can you please brief on ash sintering? You have mentioned it clearly, but for the better understanding of the viewers, I just want to ask you, what is ash sintering?
Okay. Ash, because it was a mineral and has gone through heat, it's actually lost that crystal structure. So it's actually a vitreous material when it comes out the end of the boiler. That means it's glassy in nature. When you put two materials together under heat, even if they are crystalline in nature, they will generally start to sinter together. And if you give it a long enough time, they will bond. Vitreous materials are very quick. So they will start to move together and bond very quickly. They haven't reached what we would call their liquidus temperature, the temperature where it's liquid. It happens before that. It happens as it's solid, but they will still bond together. That's sintering.
Okay, thank you. And the next thing is, you mentioned about the reflectance of, if I'm right, it is the materials?
The vitrinite reflectance?
Vitrinate reflectance. Okay, that
Yep.
indicates some nature of coal. If I'm not wrong,
The
you know what the nature is. Okay,
yeah,
we'll
the
come.
vitrinite reflectance
Yes,
gives you its rank. So
yes. But from ultimate and proximate analysis itself, we come to know about the rank. Why do we need to measure the reflectance of vitrinite?
okay, yes, you're absolutely right. The altered analysis gives you the carbon content, and that is often used to say this is a
Like
measure of rank. And the proximate analysis gives you the volatile content. Again, that's used as a measure of rank. But pretty much most standards will use the vitrinite reflectance. So it's considered the most accurate measure of rank there is.
Okay, good. And the next thing is, and the last question is, you mentioned about graphitization of char inside the reactor, right?
Yep.
Okay. After devolatilization, char is produced, right? So when it has been through the furnace, like at higher temperature for a longer period of time, you mentioned the graphitization, the tendency of graphitizing increases.
Yes.
Am I right?
Yes.
You mean to say graphitization, is that the strength of the bonds?
It's the annealing of the char. So it's actually forming more graphitic sheets within the char. So you are getting rid of any interlinking hydrocarbons between those aromatic circles,
Okay.
and any side chains. So you're extending the length of those graphitic sheets, and you're changing the distance between the sheets, so that eventually, if you left it there for an enormous long period of time or at a very, very high temperature, you would eventually get to graphite. But we don't get there in the timeframes or the temperatures that we're doing in combustion.
All right. And before the end of this session, I just want to ask one question. Right? We talk more and more about clean energy or clean coal technology. Okay. These are the technologies which is used to either mitigate carbon dioxide emission or to get a concentrated stream of carbon dioxide, as you mentioned, so that it can be easily and economically captured and sequestrated. Okay. So as far as I know, there are three modes. Like one is pre-combustion capture, another one is post-combustion capture, and the third one is we do something during combustion, like oxy-fuel technology. Which is the most promising technology that is going to take off in the near future to address carbon dioxide greenhouse gas emission?
I am more biased because all I've worked on is
Our technology.
Yeah. So yeah, I'm a very biased person. I don't think I can really be honest about that. I don't think any of them have really taken off well enough. I think, to be honest, we need to look for ways to use coal differently. And I think the renewables are really going to take off. We need to look at better storage of energy rather than looking at better ways to improve the combustion systems we have now.
But oxy-fuel technology, is it still facing the economical aspects of producing pure oxygen? Is
Yes.
that the reason why it is still in demonstration stage?
No, the problem is the sequestration. Where do you put it? Everyone is saying not in my backyard. We've really proved that oxy-fuel works. You can actually, it's more expensive than normal power, but it's not ridiculously more expensive. It's doable. We can do it now, but no one will be willing to take the sequestration. And I think that's always going to be its problem.
Right. And that's all, Liza. Thank you so much for your time. It's been a wonderful time listening to you, understanding the basics of coal and coal utilization with all the processes and basic concepts. Thank you so much for your time. I appreciate that.
Thank you for asking me. Thank you for having me. And I wish you all the best, and I hope things improve.
Thank you so much, Dr. Liza. It has been an excellent session and very informative throughout. You have touched all aspects of coal utilization and combustion. I personally felt very nostalgic listening to you. Thank you. On a closing note, I place on record my sincere appreciation to Dr. Liza Elliott for being a part of the expert lecture series organized by the Department of Mechanical Engineering. My sincere gratitude goes to all the participants. I hope that you all enjoyed the session thoroughly. On behalf of the Department of Mechanical Engineering, the faculty and students, I express my sincere gratitude to the management, the organizing team, and everyone associated with us. My sincere thanks goes to Mr. Jason, our student volunteer, for the web screen presentation throughout the series. It has been a pleasure being interacting with you all again. Thank you one and all. Please keep visiting this channel and make use of the archived webinar videos. If you have subscribed to this channel, FXCC Mechanical, you will be notified about our future initiatives. Until then, take care. Better things are on the way. Good day, mate.